Instruments, Part 1. Absolute pressure is measured against a vacuum. That is, if you have an absolute pressure gauge and it's reading 0, it means there's absolutely no molecules pushing on it. That is, it would read 0, say, in space. If you taped a pressure gauge to the side of the space shuttle, blasted it off into orbit, and it's in space, it would go from a high reading, because there's pressure, down to 0 by the time you got into space. Altimeter is actually an absolute pressure gauge, but it's calibrated in reverse. It's calibrated to read low altitude under high pressure, and it's calibrated, that is, at sea level. It shows 0 feet, but that's really at a high pressure, 29.92 inches of mercury if it was a standard day. However, if you duct taped an altimeter to the side of the space shuttle and started going towards a vacuum, it would read higher and higher and higher. And if you had a magic altimeter that didn't break, it would read infinitely high as you got into space and there was no pressure. So, of course, here's the Colesman window, and it doesn't quite read 29 or 902. Of course, hopefully you've seen an altimeter before. Manifold absolute pressure, MAP, is talking about the manifold pressure gauge on piston-powered airplanes that have constant speed propellers. But MAP is a 3-letter abbreviation for manifold absolute pressure. Here's a picture of a manifold pressure gauge out of a Robinson R22. Now this engine isn't running, so it's reading outside air pressure, and you can tell that it's just a little bit below 30 inches, so it's probably pretty close to a standard day near sea level. And this manifold pressure gauge has a red line because they've derated the engine to produce less power than it actually can. That way it'll last a lot longer without failure. Gauge pressure, just so you know, GAGE and GAUGE are both pronounced the same, and they have the exact same meaning. I usually spell things gauge because I don't have to remember which comes first, the A or the U, although I guess in alphabetical order A comes first, so maybe there is a way to remember it. Gauge pressure gauges display a temperature, display a pressure that is whatever is above the existing atmospheric pressure. A typical example is a tire pressure gauge, and these will read 0 whether you're at sea level or you're at 5,000 feet pressure altitude or at 10,000 feet pressure altitude. It's because there's actually a hole underneath in the back so that it can always reference itself to atmospheric pressure. And that works out pretty good for a tire pressure gauge, because on the tire pressure gauge you want to know what's the pressure inside of the tire compared to the pressure on the outside of the tire. Piston engine oil pressure gauges are also typically set up this way. Here's one out of a Cessna, and you'll notice that nothing's getting to it. This is actually taken out of an airplane, and it's up here reading 0. Again, it has a hole drilled in the back of the gauge so that the gauge knows what atmospheric is, and of course that's the pressure inside of a piston engine. It's vented to atmosphere, so you want to know what's the pressure of the inside of the oil system compared to outside atmospheric again. And hydraulic pressure is typically the same as well. Here we got a hydraulic pressure gauge. This one is probably supposed to be at 3,000 psi. We've got here psi times 1,000, and there's a red arc. It's really bad if it's below 2,000. We got caution between 2,000 and 2,400, and we got caution between 3,100 and 3,500, and of course the lovely green arc between 2,400 and 3,100. And hydraulic pressure gauges are also a common gauge pressure gauge. Differential pressure, my personal favorite, is where you have two pressures that are changing at any moment, and you need to know the difference or the ratio between them. Airspeed indicators, for instance. Here's an airspeed indicator. Airspeed indicators take the outside air pressure and compare it to the pressure inside of the pitot tube. So if you have a pitot tube coming in here, we're going to have ram pressure, and we're already going to have static pressure in there, and it's going to compare it to a static port. And essentially the airspeed indicator is just going to take ram plus static, subtract static. That's going to give you ram pressure, but instead of displaying a pressure in psi or inches of mercury, it's calibrated to read it in indicated airspeed. Engine pressure ratio. If you're flying jets, or you want to fly jets, this is going to be important. Here we got a jet engine, combustion chambers, air's coming in, air's blowing out the tailpipe. I need a longer exhaust pipe here. And there's going to be a probe. And air's going to get in that little tiny hole, and there's going to be a probe in the tailpipe, and air's going to get pushed into there. Now when the engine's running, hopefully the pressure in here is really high, static pressure, and the dynamic pressure or velocity is also going to be really high, and hopefully in here the velocity or pressure dynamic is going to be smaller and the pressure static is going to be smaller. So this side here is always going to be larger pressure. And so effectively it's going to be the pressure right here, pressure in the exhaust, pressure total in the exhaust, pressure total in the intake. But this is going to be a ratio. It's going to divide it instead of airspeed where it's a minus sign or a difference. And we're always going to change every time this the pressure in here is going to be static plus RAM, and the pressure in the EPR probe in the tailpipe is going to be static pressure plus RAM. And all this total here and this total here could all be changing. These two pressures could be changing all the time. In this case, we're just using a ratio of two different pressures. So here's an EPR gauge. It reads 1.01. That's just a hair over 1. There should be a dot right there. And as you push the power lever forward in a jet, the ratio of these total pressures goes up. And here's a bug. So this is saying it's going to be about 1.9 for takeoff, probably is what that's being used for. Turbine engine oil pressure. See, I need some space to draw in. Here we go. Turbine engine oil pressure. Again, we got a jet engine. And we have bearings holding the shaft in place. And we're going to have some reservoir. And we're actually going to need a pump running off of the engine to suck oil out of the engine and then pump it to the bearings. And there's going to be another pump, a scavenge pump, that sucks the oil back, and pumps it into the engine. And a lot of times on jet engines we take bleed air off of the compressor and pump it into the bearing chambers, and this bleed air is going to go through the scavenge pump in here into the reservoir, and it's going to pressurize the oil reservoir. And so it's also going to be pressurizing the bearing chambers. So let's just say that it's 50 psi coming from the engine compressor pumping into these oil bearing chambers. If the main power pump, the main pressure pump, pumps it in at a 150 minus the existing pressure, means we only have a difference. You notice it's a minus sign. We only have a difference of 100 psi, and that's very typical with jet engine oil pressure gauges, since we're going to pump air into the bearing chambers, that we're going to need to know the difference between these two pressures. And so it's very common for jet engine oil pressure gauges. It's very common for jet engine oil pressure gauges to be differential pressure gauges. Of course, here's the low red line, here's the high red line. Altimeters. And of course everybody knows about altimeter settings. They're for non-standard pressure correction. Of course I already mentioned the Colesman window. So you can correct the altimeter for non-standard pressure. Now what a lot of people don't understand or realize or think about or have heard about is that you really need a temperature correction. Fortunately, temperature doesn't go that far off, and if you're up in the air you don't worry about it too much, because if everybody has the same altimeter setting, then everybody's going to be off a little bit. But generally speaking, we don't have in aviation a way to correct for that non-standard temperature. However, if you're going to be landing where it's really, really hot or really, really cold and it's IFR, you may want to look up non-standard temperature correction, because your missed approach point might be a little higher or a little lower than you might have thought. But generally we don't use standard temperature correction factors. Automatic altitude reporting systems, essentially that's your encoding altimeter. That's if you rotate the switch on your transponder to altitude, and that's essentially transmitting the pressure inside. Correction, it's transmitting the pressure altitude inside of your static system, and it's rounded to the nearest 100 feet. So let's say you're at 5,500 feet pressure altitude inside of the static port, inside of the static system. It's going to get rid of this 0, and it's going to transmit 550. It's not even going to transmit that one. It's going to transmit 055, and of course the air traffic control computers are going to put the comma in the right place. So you could go, if it transmitted 999, that would be 99,900 feet. It rounds it to the nearest 0. It rounds it, or corrects it to the nearest 100. And it's what's inside the static port. So if you set in the wrong altimeter setting in your altimeter, your encoding altimeter transmitting your altitude rounded to the nearest 100 feet is still going to transmit the pressure altitude inside of your static port. Radio altimeter, radar altimeter, it means the same thing. It's essentially telling you AGL information. This is a radar altimeter out of an F-4 Phantom jet fighter, and it actually, as you're flying along, it sends down a radar wave, and it bounces back up, and it measures the time. So that's how it's giving you AGL. You typically don't find these in smaller airplanes. Manifold pressure is found on piston-powered airplanes that have constant speed propellers, so that way you can set the power with the manifold pressure while the RPM stays constant. On a standard day at sea level, you can measure pressure different ways, and of course you might put like that. It might say 29.92 inches of mercury. Hg is the Latin abbreviation for mercury. 29.92 inches of mercury is the pressure on a standard day at sea level. You could also call this, if you're outside of the United States, altimeter settings are going to be in millibars. The altimeter setting would be 1013, and of course that's 17. That's also equal to 14.73 psi, and of course we already know 14.73 versus 29.92 is really, really close to 2. Temperature, of course, you've known this. Hopefully, on a standard day at sea level, it's 15 degrees Celsius and also 59 degrees Fahrenheit. At 36,000 feet, standard day is minus 56 degrees Celsius. And in fact, that works really well. If we're at sea level and we go up to 36,000 feet, we know that it's 15 degrees Celsius. And every 1,000 feet, there's a 2 degrees Celsius change standard adiabatic lapse rate, and this is almost perfect. It only is off by like 2 degrees all the way up to 36,000 feet. Interestingly enough, though, at 36,000 feet, I think it's there, it's the isotherm, and the isotherm goes all the way up to 66,000 feet. It varies a little depending on what book you read, but it's from 36,000 feet, it's minus 56 degrees Celsius, and it stays that way all the way up to 66,000 feet. It's still minus 56 degrees Celsius. So from sea level up to 36,000 feet, we have a 2 degrees Celsius change. 2 degrees Celsius per 1,000 feet. So at 5,000 feet, we could figure it out. It's really nice and easy. It's 15 degrees Celsius. We go up 5,000 feet. 5 times 2 is 10. So 10 from 15 is 5 degrees. So at 5,000 feet, it ought to be 5 degrees Celsius. Of course, that's on a standard day. Of course, now we're not talking about sea level. So the isotherm is from 36 to 66,000 feet. And of course, this is on a standard day. It's minus 56 for that solid 30,000 feet in there. The Armstrong line, interestingly enough, is based on pressure, and it's at about 64,000 feet. At 64,000 feet. What's interesting, if you've ever made brownies or a cake at high altitude, you read the high altitude directions, it'll say do something different, put in a little less or more oil or water or flour, maybe cook it at a different temperature. It's because the temperature, I'm sure it has something to do with pressure, but it's also the temperature of water boils differently at different pressures. At sea level, water boils at 212 degrees Fahrenheit, which is 100 degrees Celsius. And as we go up in altitude, the boiling point of water gets less. In fact, if we go all the way to 64,000 feet, the boiling point of water here is 37 degrees Celsius. Interestingly enough, 37 degrees Celsius is 98.6 degrees Fahrenheit. This probably sounds familiar because your blood stream, most people's temperature is at about 98.6 degrees Fahrenheit. What that means is if you're above 64,000 feet, let's say you're flying along here at 75,000 feet, like we all would like to do sometime, and the airplane depressurized, the pressure isn't going to keep the water in a liquid state anymore. It's going to start trying to expand to a vaporous state. And interestingly enough, the ratio of expansion from liquid to water is 1 liter of water is going to turn into 1,700 liters of vapor. So your body is going to try to expand quite a bit. I think it probably wouldn't be very pleasant. So if you're above the Armstrong line, you probably ought to wear a spacesuit and have a pressurized cabin. That way, in case you depressurize, your spacesuit will save you. And of course, we know that the rule of thumb from sea level goes up to about 15,000 feet. 1,000 feet of altitude gives you 1 inch of mercury less. So at sea level, if it's 29.92, and we come all the way up here to 5,000 feet, we can take 29.92, subtract 5, this 5 right here, and we get 24.92, and that would be the approximate outside air pressure in inches of mercury at 5,000 feet on a standard day. Of course, every day is not 29.92. What's really cool is you can actually take the altimeter setting and do this and check out and see if your manifold pressure gauge is accurate. So let's just say you're at sea level and the altimeter setting is 29.92. This makes it really easy. So 29.92 minus 0, because we're at sea level, is going to be 29.92. So our manifold absolute pressure gauge on our reciprocating engine airplane with constant speed propeller, the needle's going to point to 29.92. Now let's just say we're at 5,000 feet. And let's say the altimeter setting is not 29.92. Let's say the altimeter setting is 30.20. 30.20 minus 5,000 feet. 0 to 25. Now, this is what the manifold pressure gauge is going to read during pre-flight when the engine's not running. The gauge is going to read 25.2. So we can take the altimeter setting and then subtract our mean sea level, above mean sea level altitude, and if it was like 5,200, then we'd have 2500. We can subtract that altitude, and it'll give us, essentially, this is barometric pressure. It's our outside existing barometric pressure. And that's exactly what the manifold pressure gauge is reading. It's an absolute pressure gauge, hence the term manifold absolute pressure. Yeah, I got a hand set. Now, takeoff becomes rather fun. Let's say we're going to take off. Let's try it again. So let's say we're at a 7,500 foot airport, and the altimeter setting is 28.50. We'll make it easy. So 28.50 minus 7,500 feet is 28 inches of mercury, is what it ought to read on pre-flight. But you got to understand that reciprocating engines, the piston goes down and pulls in the air into the engine. So the air going into the engine has to get sucked in, so the pressure is just a little bit lower. It's a little bit lower. It's about 1.5 plus or minus 0.5, less than that. So 21 minus 1.5 would be 19.5 plus or minus 0.5. Another way to describe that would be 19 to 20 inches of mercury. So this is what the engine would read on takeoff if it was normally aspirated. Normally aspirated means that it does not have a turbocharger or a supercharger. So we've got to take into this correction factor, we've got to subtract 1.5 inches of mercury plus or minus 0.5, or you could say it's somewhere between 1 and 2 inches less than barometric because it's having to pull the air in. So now, if you're flying a normally aspirated piston engine, if you've checked the manifold pressure accuracy before takeoff, before you start the engine rather, now you can do this one additional calculation and subtract 1.5, subtract 1 or 2, and now you know exactly what the manifold pressure gauge ought to read during takeoff to tell you whether or not you're developing takeoff power. Yay! Now, here's another interesting thought. What if you're turbocharged? Again, let's just say you're at 3,500 feet airport altitude and your altimeter setting is 29.00. So 29.00 minus 3,500. You're going to read 25.50 inches of mercury during pre-flight. But if you have a gauge that looks like this gauge right here, it's got a red line on it. So this is telling me, when I found this on the internet, that this is turbocharged. What's going to happen is, and this is off a twin-engine airplane, it's hard to see, but there's 2 arrows in there, number 1 and number 2. And so this gauge is taken out of the aircraft, and it's showing a little over 22 inches. So that's telling me it's not on the standard day at sea level. It's probably at a high-altitude airport where this was taken. But in a turbocharged airplane, you push the throttle all the way up to the red line. So you don't have to calculate what should the takeoff manifold pressure gauge be. If it's a turbocharged airplane, it should come up to the red line. Hey. Okay, airspeed indicators. Of course, I already covered the fact that airspeed indication takes the pitot pressure, which is really static plus ram, and subtracts the static to give us ram. But it's really calibrated and indicated airspeed instead of PSI or inches of mercury. If you want to do true airspeed, of course you've tried this before. Oops, I know I have a picture in here. Oh, didn't have a picture in there. True airspeed, you can correct it for temperature and altitude, just like on those airspeed indicators, or you can do it with your whiz wheel. You have to say, okay, I'm at this pressure altitude and I'm at this temperature, and it'll change. Essentially, the higher you go in altitude in general, true airspeed gets higher compared to indicated. So at altitude, you might be showing 100 knots indicated, but you might be doing 120 knots true. Now, you only have to get indicated airspeed to go to true airspeed by using temperature and pressure altitude until you're flying close to Mach 1. As soon as you get to close to Mach 1, you're going to have to take into account temperature and altitude and compression, or we'll say compressibility. Look at that, 3 I's in a row. Compressibility. As you're flying along, if you got a static port coming in the wing, if you're flying up, like 0.7, 0.8, 0.9 Mach, it's going to be pushing the air in here and it's going to compress it. And so you're going to get a higher pressure than you would otherwise. So you're going to have to take this into account if you're flying close to Mach 1. All right, now, VMO, velocity of maximum operation. Velocity of maximum operation. Let's say, here's actually a picture. I've retouched it to make it look a little more clear. This is an airspeed indicator out of a Boeing 757 on the ground. Right now, it's showing 30 knots indicated airspeed. This is just a repeater in digital form for the airspeed indicator. Of course, it's probably just taxiing into the wind. And this is the red line. But you'll notice this red line is a barber pole instead of a solid red line. And it actually moves. It's not painted on the gauge like it is in a smaller aircraft. You're only going to see VMO gauges in aircraft that are going 0.6 Mach or higher. So if you're going to be flying a transport category jet, big biz jet, big turboprop, you're probably going to see an airplane that's got VMO. Now at low speeds, all you really have to do is worry about flying so fast that you bend the airframe. So you notice right here, here's 300, 310, 320, 330, 340. This right here, this looks about 345 knots indicated airspeed at low altitude. And this is out at Phoenix Airport, so it's down at 1700. So you could go really, really fast, 345 knots indicated airspeed, but of course below 10,000 feet, we're not supposed to go faster than 250 knots. Okay, so that's so fine. What's the big deal? Here is this same exact gauge at cruise. Now we're doing 277 knots indicated airspeed, which is just a repeater for this gauge right here. Here's 250, 260, 270. Sure enough, there's 277, but this is also shows Mach. This has a Mach meter, 0.813. Now this airplane probably has a red line of 0.82 or 0.83, maybe 0.84. You'll notice right here, this indicated this barber pole, or VMO, it went from 347. It's all the way down here. There's 280, 290. It looks like now it's doing about 293 knots indicated airspeed. It got lower at altitude. VMO gets lower at higher altitudes. And the reason for that is because you're coming up against Mach. You would have to get up to that 200 or 347 knots indicated airspeed before you bend to the airplane. But now we've actually reduced it by more than 50 knot reduction. And it's because of negative Mach effects. So I'm going to say that. I'm going to have to draw you a picture. I need to get a clear screen here. Negative Mach effects. There, we're going to go with the E. Negative Mach effects. All right, so let's say we got our transport category jet with our asymmetrical wing, and there's somebody here in the cockpit flying the plane. Got a tail. Let's put the tail down here. Now, as you're flying along, the airflow is going to go above the wing and below the wing. And of course, if the airspeed is, say, Mach 0.80, we'll use the FAA's definition. The FAA says the transonic range is 0.75. So let's say we're going Mach 0.75. And so this airspeed underneath the wing is going Mach 0.075. But the airflow on the top of the wing is going to go faster. And it's very possible that right here we'll have Mach 1.0. And we're going to have a little shock wave and some turbulence, and it may reduce the effectiveness of the tail. If we go faster and faster and faster, so instead of going 0.75, we go Mach 0.85, this turbulence could be enough that the tail becomes ineffective. And of course the tail is holding the airplane down, so if the tail goes up, the nose of the airplane would go down. This is called tuck under. Tuck under is when you lose effectiveness of the horizontal stabilizer. It doesn't keep the tail down anymore. The nose goes down and uncontrollably. And of course, if the elevator's not doing any good, you can't stop it. And of course, when the nose goes down, you go even faster and makes it worse. Don't you hate that? The other thing is called flight control buzz. Oops. Flight control buzz. Let's take a closer look at a wing. And here's an aileron. So if we've got a shock wave because the airflow across the bottom is 0.75 and the airflow across the top is 1.0. We've got a little turbulence going on. This turbulence is going to affect this aileron. I can't spell aileron. Okay. And so the aileron is going to vibrate up and down a little tiny bit. And if you're in an old school airplane where this is controlled by cable, you could actually feel it on the control in your hand. Or if you're in a business jet that still has control cables, you're going to feel some of that buzz. It's okay to fly fast enough so that you have a shock wave and you have turbulent airflow going across the tail, and it's okay to fly fast enough that you got a shock wave that you get some flight control buzz. The transonic range, according to the FAA, is 0.75 to 1.25, and most red lines for transport category jets is somewhere around 0.84, 85, something like that. Which means the transonic range, the beginning of the transonic range, 0.75 is the lowest forward speed of the aircraft, where somewhere on the airframe you're getting Mach 1. So even if we're cruising along at Mach 0.75, the airflow across the top of the wing at some point could be Mach 1.0. We're flying in the transonic range. It is normal to fly inside the transonic range and have these effects going on. But if they get too bad because we go too fast, then we're going to be really, really unhappy. The aileron could become ineffective as well if this got too bad. So that's why we have wrong direction. That's why we have a VMO gauge is at high airspeeds. At high airspeeds, this line right here is going to keep us below a Mach number that will have negative Mach effects so bad that we'll lose control of the airplane. If we let the indicated airspeed go higher than VMO, then those negative Mach effects will be so bad that we could lose control of the airplane. We're not going to bend the airplane till we get a lot higher. That's not what we're worried about. At high altitude, we're worried about about making sure that the negative Mach effects don't go so bad that we lose control of the airplane. At low altitude, we're worried about bending the airplane. And of course, Mach. The only thing in the Earth's atmosphere that changes Mach is temperature. And so if you have a Mach meter inside of the airplane, you're going to have a temperature probe stuck out on the side of the airplane so your Mach meter or your air data computer can calculate what your Mach is based on your static pressure and your pitot pressure. Oh, there was that true airspeed indicator where you can rotate this knob and you would set temperature to pressure altitude. I must have inserted it in the wrong place. I'll get over it. Okay, pitotstatic systems. Of course, this is pretty, you've seen all this before. There's a pitot tube for a 172. Here's some pitot tubes for some fast jets. Of course, we've already covered it. Inside the pitot tube is the static and the ram pressures. And you're going to send this pressure to airspeed indicators. You're going to send it to Mach meters. If you have some kind of a warning system, like for stall or for Mach overspeed, that system is going to need this pressure. And ADC stands for Air Data Computer, and you'll learn a lot more about that sort of thing when you take the AS358 Advanced Avionics. But that pressure in the pitot tube is going to have to go to, 4 different places if you're in a transport category jet, big biz jet, big turboprop. The static port, of course, here's one off of 172. Here's one off of a big honkin' jet. It actually says captain, and here it says first officer, so there's actually 2 static ports on this airplane, at least on that side of the airplane. Of course, it's only static pressure, but you're going to send it to a lot of places. Of course, the airspeed indicator needs both the pitot pressure and the static pressure to decide what airspeed you're going at. Same thing, the Mach meter is going to need both pressures, and if you've got a Mach warning or stall warning based on airspeed, it's going to need both of them. And of course, your altimeter and your vertical speed or rate of climb, those need static pressure. Of course, that's just a review for most of you. And of course, the air data computer. Air data computer is going to calculate a bunch of stuff. It's going to calculate true airspeed, Mach. It's going to calculate a lot of information to send to the flight computer that's flying the airplane. And here's a really fun one: the cabin differential gauge, the cabin differential pressure gauge. Remember, that's the pressure on the inside of the airplane divided by the pressure, or subtracted from the, and then you subtract the pressure on the outside. So if you've got 11 psi on the inside and there's 2 psi on the outside, you'd have a 9 psi differential. So this outside pressure, hey, that's what's going to be in your static port. If you're flying a large aircraft, of course, if it's certificated for known icing, you're going to need more than one Pitotstatic system. And if you've got an air data computer, so here's an air data computer, here is a static port. Goes to the air data computer, and this one is set up to have static ports on both sides, so it averages them, so they get more accurate. And here's the aircraft commander. Here's the captain. Captain, static port. Goes to the rate of climb, the altimeter, the Mach meter, and the indicated airspeed indicator. Static port, and of course the captain has one on that side too. I guess I could use different colors. Yeah, sweet. So the co-pilot has a static port on each side of the airplane, and that goes to the co-pilot's rate of climb, altimeter, Mach meter, and indicated airspeed indicator. So we got static. Oh wait, and I forgot, the static system also goes, this other static system also goes to the cabin differential pressure gauge. Then we're going to have pitot tubes. Aircraft commander's pitot tube goes to the indicated airspeed and to the Mach meter. Co-pilot's pitot tube, goes into a Mach warning system, indicated airspeed, Mach meter. And then look, here's a third pitot tube which runs the air data computer and another separate Mach overspeed warning system. So on a transport category jet, big bizjet, big turboprop, you're going to need more than two, commonly three Pitotstatic systems to run the captain's gauges separately from the first officer's gauges, separately from the air data computer, so that if any one quits, then you still have another two sets of really good, accurate information. You know about the connections. Any questions, improvements, you know how to get a hold of me. Thank you very much.